Yeah, we'll do. Thanks so much, Steve. And thanks everyone for your patience. Yeah, we usually give it about 5 minutes at the beginning just to get everyone settled anyway. But the man of the hour, Thomas, is here, so we'll get started. Yeah, with webinars, they're kind of like one way. Like we like them to be quite interactive, so that's why we've got the Q&A button at the bottom there. So please ask a question at any time. I'll be glancing over and we'll try and answer your questions live. We also have the Q&A at the end as well, so like feel free to just drop your questions in at any time. And yeah, keep those coming in. So yeah, I'll get started now. So you're here because you want to learn about industrial companies, how they're consolidating high frequency sensor data, and how they're able to do monitoring and analytics much better as a result. So first we'll do a few intros. So I'm Tun Shui. I look after data and DevRel here at Quix. I've got a background in data engineering. I've worked in analytics engineering as well with data warehouses. So I'm used to working with data all over the place. I've recently kind of stepped more into strategic roles. So as a manager and as a VP, helping other companies get up to speed with different types of data, different types of architectures, usually with stream processing somewhere in the mix as well. And my areas of interest are definitely around the AI ecosystem, which is continuously growing. Of course, real-time data. And when I'm not doing that, you're going to find me either in the sea or in the gym. And I love coffee, cameras, and guitars. That's important information for later. So now that Thomas is here, I'll hand it over to Thomas. Do you want to do an intro?
Yeah, hello everyone. Glad you come here, guys. So my background is software engineering, and I spent my whole career working with real-time data, mostly sensor data from cars and things that move around the world. And I work in F1, where it's kind of the most extreme use case of sensor data, connecting F1 cars to data platform. And when I'm not working, I like to cycle, ski, coffee, cameras, well, these sort of things. Yeah, that's me.
Yeah, nice one. Thanks. Yeah, and I guess the people here who are attending are going to see a lot of parallels between critical environments like in Formula One racing and in industry because it's all about fast data. So I'll move on to the next slide, which yeah, let you talk a bit about the F1 racing background. What kind of data scale are we talking about? What are the different types of data that you saw in F1?
Sure. So yeah, so in a F1, every car has around 300 sensors on the car, and then on board from 300, they calculate around 70,000 different um, parameters, and then send them then over the radio to the pit where from the pit we send it to the platform, and some of them are very high resolution. So, for example, the gearbox parameter could be over 1 kilohertz, which means more than 1,000 numerical values per second. And so what I was doing in Macro and with my team was to try to get this into a common place. And so domain experts and people that understand aero, chassis, etc., mechanical engineers will be able to build real-time decision insights and analyze the data. And so we use Kafka and Kubernetes and the latest sort of distributed systems to make that happen. And where we thought that uh, the mission is completed, and now everybody's going to use this data to build these insights. But the problem was that this technology was not really compatible with sort of end user, which was the domain expert working in Python, Jupyter Notebooks, MATLAB, um, and using Kafka, Kubernetes, and Docker. That wasn't really compatible. So this is where we kind of saw for the first time that there is a gap how to use this and leverage these technologies. So yeah, the rest is the history, and we found it quick. So yeah, that's sort of our F1 story.
Yeah, there's like so many sensors. I remember the metrics. It was like 300 onboard sensors, each firing at between 100 hertz, but they can go up to like 4,000 hertz. So that's a lot of data.
Yeah.
So that's a really interesting background you've got there. Cool. Okay. So as I mentioned, so the Q&A is always open. So please drop your questions in there if you think of a question, or you can save your questions for the Q&A at the end, which we'll do. But here's the overview. We're going to talk a bit about why companies are consolidating data, the benefits that come with it, and get into a bit of like the technical details around how you design to deal with high volumes of data. So, why are industrial companies consolidating data? So, when we talk about data here in this context, we're talking about high frequency sensor data and we're talking about time series data. So, time series data is basically any sort of data that happens that is generated in an interval and has a timestamp. And together, all these data points form a series of measurements. That's the simplest way to put it. Usually, time series data in these industrial settings, you get a high volume, a high throughput. So, they're coming through fast and hard. And a lot of these industrial systems, everything from energy systems to anything that does condition monitoring around temperature and pressure, like these systems generate loads and loads of data. And the reason why you should consolidate all this data is you want visibility across the whole organization. So a lot of the industrial companies work with two kind of broad departments. There's operational technology and there's information technology. And it's the constant kind of sharing of data between these two kind of like parts of the business. The IT part is always concerned with the analytics and building things like machine learning models and predictive analytics around it. And so you're going to make sure that you move the data and make it available for everyone. And to do that, you want to create a single source of truth and you want to retain as many data points as possible. Thomas, I was just wondering, like, because you work quite a lot with our customers as well. Are these the sort of things that push people to consolidate data? Can you think of anything else?
Well, definitely the problem is how to work with the data in that are moving and the data that are at rest. Also, the data coming in are probably quite often in protocol that are not really great to be used for analytics and for persistence as well. So the consolidation really enable the rest of the company to leverage the data. So what we see in the customers is that the data coming in are very choppy in terms of sensors not coming together, coming in different frequencies, coming not aligned in terms of time. Some sensors coming late, and sometimes the amount of data is just too great for visualization analytics. That's where the high resolution time series data has to be downsampled, for example.
Cool. Okay, makes sense. And we'll get into some of the use cases that this data consolidation enables. And what that means is you can do things like real-time analytics, which will enable you to do real-time alerting. So you don't have to wait for the top of the hour or kind of like a daily report. You kind of get these alerts pushed out to you in real time. You've got things like different models around, you've got stats models, you've got machine learning models. So anyone that has data science teams or any sort of capability that they've built in Python, this will make it much more straightforward for you to build out predictive maintenance, things like digital twins as well. So overall, the innovation is just going to be there for you and you're going to be able to develop much faster. And at the heart of it all, it's really about continuous monitoring and being able to maintain your equipment. Because for any business that relies on these machines, downtime really costs the business, and you want to avoid that as much as you can. The traditional way is when you do daily reporting, you do regular checkups where someone with a clipboard goes around and they have a checklist and they check the equipment and they make sure that everything looks fine. This is obviously time consuming. It's not an exact science. I mentioned I like coffee earlier, so I have an espresso machine, so that requires some maintenance. So for all of you out there who have espresso machines, you know that you need to make sure that you have some daily cleaning, but maybe like once a month you need to do a deeper clean. I do it manually by putting it into a calendar for me. So I have a calendar reminder that pops up and then I go and do it. But it would be so cool if I could just attach sensors to, like the pump, for example, and have temperature sensors, like things like that. I think those are actually available anyway for your coffee machine, but I should go down the path of exploring that, and that will enable me to maintain my equipment by looking at data points over a period and spotting the trends. And that's kind of like how these industrial machines work these days. A lot of the more modern equipment will come, with sensors. You can also retrofit sensors to legacy equipment, so you can really, have this opportunity to have real-time checks and start building out models for predictive maintenance. But before all that, of course, that data needs to be available in a central place. Otherwise, you just can't process it all together. And I'm going to go over some of the challenges in monitoring and analyzing sensor data. So, like this particular webinar is going to be in a series of a few webinars. So we're addressing the one at the bottom here. So that first column is like the jobs to be done column. These are the common tasks that we're seeing in industry. And on the right-hand side, that column's all about the various challenges that come out of those common use cases that you see. So we're addressing the one at the bottom there. So yeah, have a look if you like any of the others, or you can think of new ones, or you like to talk about new ones that we haven't even mentioned that you'd like us to cover, then please get in touch or drop it in the Q&A and we'll pick it up from there. So let's move on to the challenges. So handling continuous and low latency data, that's going to be important because you have to handle real-time data. So as soon as these sensors are, as soon as that data is generated, these sensors need to be transmitting that data and doing something with it, processing it. And often at times, especially if you're a larger company or you have several like different factories and plants, you're going to be handling a lot of data all concurrently at the same time. So these are sort of challenges. We have things like thousands of concurrent sensors. Like Thomas, like you mentioned, like in F1, and even in some of our customers, they have like hundreds to thousands of sensors going on at the same time, right? So we're talking loads of data points. What kind of data are we talking about? Like, what's the shape of the data? Is it quite lots of parameters, quite fast data? Like, what are you seeing out there?
Yeah, so we see basically both extremes. So one extreme is that you're looking for very high resolution data in a short amount of time. That could be the F1, for example, when in 1 hour you're looking at sensor data that have more than 1,000 values per second, and you're looking at the thousands different sensors. But then the other extreme would be manufacturing projects where, and use cases where you might have a lower frequency of data. So let's say 1 second granularity for your sensors, but you're looking at the quarters. So you want to see 3 months and different sort of trends in your data. And then at the end of the day, you're looking at roughly the same amount of data points. And this is where the challenge with working with this data coming from. You simply working with millions of data points, and whether that's a database or your visualization will struggle when you're going to try to put millions or hundreds of millions of data into a query or into some sort of waveform. So this is where the challenge coming from, one of the biggest challenge. The second challenge is obviously when you try to mitigate this amount of data and go into something like a downsampling, for example, then data are not always coming in a nice format, not always coming aligned, and sometimes you're getting gaps. And this is the second challenge, how to deal with these problems.
Yeah, wonderful, thank you. So yeah, on the next slide, we kind of go into some of that. So yeah, when you silo that data, you'll find that at the edge, a lot of that processing is done and the insights are obtained, and then that data doesn't get transmitted anywhere else. So, you know, the other data teams, other sensors don't know about these insights. So it's always happening in isolation. So that's a real challenge, surfacing those insights globally, like across the business, especially. Thomas mentioned maintaining data quality and also data visualization. Like those are difficult things to utilize. Like we have great tools that let you visualize data, but when you have too many data points, when you try to make sense of it, it's always like a challenge. And it's different with every sensor, with every customer. Like the variability of data formats, you wouldn't believe. There's so many different types. So yeah, it's really a case by case basis. But you can take the same mindset to each of these problems and solve them in the same way. So let's talk about some of these data consolidation techniques. So I keep saying data consolidation, so I should be clear on what I mean by that. So consolidating means just to collect it all in one place. And I've been talking about putting it into a central hub. So this is the kind of reference architecture we see very commonly. So we have all these programmable logic controllers, all these like sensors or gateways from factories and different plants that are transmitting that data. So they might have edge databases like InfluxDB, for example, or other sorts of time series databases. We see lots of different technologies there. They go into a centralized data system similar to Quix, or they might be building their own. Some of our larger customers have fully loaded software engineering teams that build on Azure, GCP, and AWS. So they'll be building out that centralized data system. And that's where all of the pre-processing happens. So you've got things like downsampling, normalization, feature engineering for your data science teams. All of that stuff happens, and it enables your alerting, your predictive maintenance, things like digital twins too. And then you've got the arrow there which goes to a data sync. So we will sync out that data to any other data store. So any other database, data warehouse, any other system that needs like that is owned by a team that needs that data. So that could be a business insights team, for example, that wants to understand some of the operations. So it's really flexible to have this sort of architecture where you have all these syncs in parallel that can basically get a copy of that same data like locally in a team and be able to deal with it. So that's basically like how you basically build this capability. You just have all that data in one place. So for pre-processing high frequency data, we're talking about data normalization. So that's kind of like what Thomas alluded to. You've got data that's in different formats, different schemas. They come in at different intervals, and you want to be able to compare them like for like. And to do that, you have to standardize it. And that's what data normalization is. You're doing lots of other things like removing bias as well. You're removing kind of corrupt data. You're kind of like handling anything that's missing. So you're imputing like new values in columns, things like that. So that's what normalization is. With downsampling, you're taking basically big amounts of data and you're making it smaller, and you're doing that by preserving the crucial kind of the crucial information in that the integral parts of those measurements have to be preserved when you're doing downsampling because it's essentially a loss of data, but you got to do it in the right way. So that's always a challenge. And we do it largely using a time-based aggregation, meaning you do some sort of like hopping window, some sort of window function that will enable you to compute things like the average in that period. And then you distill all those data points down into a single one. And yeah, well, I mean, it's not easy to describe in words or even in illustration, but Thomas is going to show us how he does that in the demo in a bit. And these are sort of challenges. So yeah, there's a lot of computational overhead for data normalization, especially at scale. Thomas, can you speak a bit about kind of data normalization that you've seen in customers? I think you mentioned one there, like the second point where the values are really simplified, like they'll scale it to like an integer, and there needs to be some sort of
Yeah.
mapping to a value that makes sense, right? So what are the sort of things you've been seeing?
So there's a couple of things that we see. Well, first of all, the common interfaces with sensor data in industry, like for example, MQTT, has certain way of sending data over the wire. In terms of MQTT, it's the topic structure where each sensor is in a topic tree, and that's obviously far from any sort of tabular format that you want to land in a database or in your analytics. We also see that things like enums being collapsed to just the numbers to save the bandwidth. We see binary protocols that even saving the bandwidth even more. And then because the data coming by sensor, not by unit or device, which is probably what you want to do, you have to do some data normalization where you sort of transpose the format from sensor-oriented data to maybe a device, user, or a machine-oriented stream of data. And you create a tabular structure that you can use for analysis. You can use it to persistence and then batch analysis. Also, you can expand these binary or integer numbers to a domain-specific enums. So for example, you know that 0 for this machine means stopped and 1 means running, and you can do that conversion. And you can also clean some of the known issues with the data, which are going to be domain specific to that source. So yeah, this is what we're seeing with our customers, and I'm going to show you one example where we're going to normalize the data coming from the source today.
Yeah, that's something I've seen a lot as well, like optimizing it for transport. So you want to reduce the size of the value. So you map it to, you rescale it. So a common scaler would be to turn something into a number between 0 and 1, for example, just so everything can be compared together. So that's super common. It's also common in data science as well, because it's a land that has a lot of batch processing. So it's reading all the values into memory and then processing it. And to do that, you want to reduce the amount of memory. So you just create simpler values. And then you got to do the mapping afterwards. But with stream processing, kind of like modern systems, you don't necessarily have to do that. You have compression, you've got different binary formats that help you with that, so you can do all the deserializing like on the fly as well. So it's like much more convenient. So yeah, so here are the benefits of data normalization. You get that better analysis, so everything is more meaningful because you can compare it. And then you've got improved machine learning and anomaly detection because, as Thomas mentioned, you have better persistence. Partitioning, for example, if you need to start analyzing data across, let's say, in a factory, let's say you have several factories and you want to start aggregating, so you know at the factory level, let's say the operational metrics for the batteries and their consumption in that factory. And then you could then roll it up into an aggregation across the whole region and then across, all your plants. You can do things like that without breaking out too much of a sweat. And that's all possible because of data normalization when you standardize schemas and standardize like how your data looks. And on to downsampling. So downsampling has a lot of challenges. So yeah, you have the loss of critical information sometimes, and you've got to have this big balance where you're balancing, the fine-grained analytics that you need versus the storage costs that keep going up if you keep saving everything. So yeah, Thomas, like you mentioned a bit about that. How are companies kind of finding the right balance, for example? Because obviously, if you store high frequency data, you have to then process it, which has a knock-on effect for processing costs. So how do companies out there start striking a balance to figure out how much they should store? Like basically the sample rate, like how do they determine that?
Yeah. So, well, first of all, usually, at least so far, what we have seen is that it's usually not the only one downsampling that's happening. You might have multiple different downsampling for like different window sizes. And what drives that is usually, well, first of all, how you're looking at the data. So if you're looking at data in a period of 1 hour, then probably a 1 second granularity is enough because that 1 second would convert to a pixel on a dashboard. If you're looking at the quarters or months, then maybe an hour is enough because that hour going to be 1 pixel in your waveform. The second problem is that downsampling, of course, obscure a certain anomalies in the data and might smoothen the spikes that you actually are interested in. And that's why different aggregations simultaneously happening on the data can help with retaining some of the information. So for example, instead of just downsampling data using a mean aggregation, you also package things like max and min, where then you know that in this time bucket, actually, although it looks smooth from the mean perspective, there was a huge spike going up or down. And yeah, so these two things, different aggregations and then different window sizes based on how you look at the data. What we also see with the multiple customers is that the visualization works with a different granularity of the data. So you might look at the raw data or the lowest downsampling you have when you're looking at a short period of time. But then as you're zooming out, you actually switch to bigger windows in your database so you don't stretch your time series database by downsampling 10 or 100 millions of rows just for that one view.
Yeah, it makes sense. And and in case that was lost for everyone else, like you should always go back to the requirements. Like, what are the requirements for reporting? Like, what is the granularity you need, like around that? Like, do you need to do quarterly reporting, things like that? And so, computing metrics, like Thomas mentioned, like doing some as min and max as well, like just covering a few, like covering your bases a little bit. Like sometimes when you're unsure, like that goes really far. So let's talk about the benefits as well. So you got simplified data processing overall, better dashboard performance. So you can actually make sense of that data, and you're vastly reducing those storage costs as well. So yeah, we've seen anything from 10 hertz down to 1 hertz. So that's like a massive, like substantial difference. So you're able to like unlock those kind of savings. Let's talk a bit about the architecture for managing these high data volumes then. So you've got to basically, like in that diagram before, you've got to centralize that data collection. So you've got to get those data off those sensors or those PLCs and get it into a central location. You need to have some sort of mechanism that enables you to go in a kind of incremental event-driven manner and process that centrally. And then you've got to store all that data somewhere. So for any sort of historical querying, some sort of time series database, like Thomas is going to demonstrate using InfluxDB, but there are lots of different ones out there you could use that are specialized to storing this sort of data. And then you can start thinking about like tiered storage. So where you have the hot data, which is like recent data that you're querying or data that you're querying a lot, you're going to make sure that's available versus the colder storage, the stuff that you might save in object stores somewhere else in another region, backups, things like that. And these are sort of implementation considerations. So I think Thomas is going to go over that in the demo. So I'm not going to dwell too much on what resilience and fault tolerance is. But in short, you want that data to always be available. When you're writing that data, you want to make sure that data isn't lost because that's the worst thing. And how you would scale out. So there's different ways of doing that. We prefer horizontally scaling. So adding more nodes that would take up a portion of that work. And that's the sort of thing that is a better way to scale out and is much more economical. So yes, Thomas, do you want to take it away with the demo? So I'll stop my screen share and I'll let you
Yeah.
take over.
So let me share my screen. Hopefully you can see
Yep, great.
pipeline. Great. So what I'm going to show you today is an example of a pipeline which acquire sensor data from a phone. The reason I'm using phone is that you can replicate it by yourself and clone this GitHub repo and use your phone, whether it's iPhone or Android, to send a quite a high resolution sensor data without needing any machine with the sensors. So here we have in production a simple Flask web gateway, which is doing nothing else than just exposing a simple post web API, which then means that I can, with my phone, start send data using this app. So the app looks like this. It has a different sensors you can choose from. You can choose different frequencies. So I'm using accelerometer, GPS, and battery, and I'm sending it at maximum frequency this phone can do. So here you see the message I'm getting from the phone. This is something I can't really control. This is how the author of this app decided to send me the data. So as you can see, it's a nested JSON, which contains a payload in arrays where we have different sensors with different measurements and different timestamps. Of course, that is not how I can save it to Influx databases. As Toon said, I'm going to use the time series database Influx. And also, this is not really how I can send this data to my machine learning model, which I'm going to show you in a second. So what I'm doing here is the data normalization that we have discussed in our slides. So I'm getting this sort of data from this nested JSONs in this data normalization service into a tabular format. So if I get in and show you the result is just nicely formatted columnar data, which means that now I can do things like here I can go to waveform and enable the accelerometer data. And if I shake with my phone, it's going up and down, and now it's going quiet again. So now the data are in a format that I can do something with it. So the first thing I do is that I save it to Influx. So I can later analyze it. I can use it for dashboarding, etc. So I can go now to Grafana here and go to my dashboard. And here you see I'm in a Prague in Central Europe. And if I just zoom here and keep just the green to not to go too far ahead and zoom you can see me shaking the phone. And if you focus on the time index here, on the time axis, this whole window is just 2 seconds worth of data. And yet, if I zoom even more, we see that in 50 milliseconds, we have 5 timestamps. So that's really a lot of data. And if I go to last hour, you can imagine now with a simple math how many data points from just one phone we are collecting here. And this is where this would become very quickly impractical, because I would have to start querying my database, and the database would have to be downsampling ton of data to give me this view. Also, if I don't do that, this waveform would struggle with visualization. I also have here a simple WebSocket interface, so I can show it in a web application. You can imagine you have some companion app on your phone. But if I'm going to be sending this sort of data there, this component going to very quickly struggle with the amount of data, because it's going to be millions of items very quickly in my front end. So here is where the downsampling comes to place. So the raw normalized data now comes to the 1 second aggregation. That is quite huge reduction in the data, because we're going from 100 or 200 hertz data to 1 hertz data. And here, if I go in to show you, so on input, we have normalized, but still not aligned data. So for example, the GPS data will be very scarcely present here, because we get one GPS location per 5 seconds, roughly. And we get around 200 accelerometer points per second. Very different, as you can see. And we're going to the output, where now you see we have all the data nicely in a table going from up and down. Every second we get one information. And that's why now we see battery level and the fact that my phone is unplugged. So this is where the downsampling doing its trick. If I go to the code of this service, here we supply the window size, which is 1 second from the parameter, and we supply the graceful period of 250 milliseconds. That's because if my phone would be on a poor internet, it might send some of the sensors a bit delayed. So they might arrive to the platform delayed before the other sensors, and then they will be just discarded if we don't set the graceful period. So here we're gonna wait up to quarter of the second for these late arrivals. And importantly, this is what identifies this service in the distributed in our distributed model. So we don't lose or count twice any data points, because that could be quite dangerous. If you, for example, do a cumulative sum on a sensor, if you count some number twice, you basically invalidate that information forever, because you have counted something twice. Imagine an odometer on a car. You don't want to count some data point twice. So this is all governed by Kafka and Kubernetes under the hood, abstracted away by a quick streams library. So going back, if we now enable, because as you can see here, I'm sending that 1 second downsample data to Influx as well, to different measurement. And that means here I can enable that. So if I found some interesting moment here where we were moving a lot, there we are. So if I make the yellow thing a bit more pronounced, so There we are. Now you see that the points are one per second, and this is actual points. If you zoom a bit more, it's lots of data, but the yellow thing, if I just keep it there, this is what we get in downsample data. This is the whole thing. So now we're getting a reduction factor of 200. So we're basically persisting 200 times less data into that measurement. And that means that if we go to last 24 hours, we would be able to disable the original one and get just a downsample one to get much cheaper, faster query. The second thing that this downsampling will enable us to do is to feed this data to our machine learning model here. Because if I ask the machine learning model 200 times per second, if some anomaly happen, even if I batch it, it's going to be lots of data and it's going to be expensive. So here I'm just doing it once per second and listening for results, which means that if I go back to my front end and I try to mimic the situation where I drop my phone. The power of the demo. Let's see. Yeah. So somehow that demo didn't work out. Well, we will see the event here if it worked. But oh, now it detected. Great. So maybe I was shaking with the phone in a way that was not really detected by the model. But now you see that there's a drop detected in my pipeline. Unfortunately, now I don't have a GPS signal, which is a shame. But I had before, and now you can see that in Prague, the event happened. Great. So now this is done by this model that is just getting the 1 second granularity, and as a result, consuming much less CPU and memory than it have to if it would be connected to the raw source. Yeah, the last thing I can do to show you where I can leverage the downsampling and consolidation of my data, I can reconnect this WebSocket service to downsample data as well, which would make the WebSocket service much more lightweight, but also my front-end application will be much more happy because as you can see here, this is just getting too much data. We can't even visualize in this front end. So we wait for this to start, great, and we refresh this thing. So now this will get much less data. Great. So now you see it's getting 1 second informations, which is maybe not as stylish as the 200 hertz sensor readout, but this is actually more sustainable for application like that. So now you see when I move with my phone, it's going up and down. So this is using significantly less resources than it used before. So this is the pipeline that is in the GitHub. We're gonna share the link so you can clone it, fork it, and with your phone replicate exactly what I have done here with literally no coding because everything I have done here is in that repo. So feel free to give it a go. And if you have any questions, even after this webinar, you can ask us any question on our Slack because we have community Slack where we can discuss details of this pipeline or any other.
Great. Thank you very much, Thomas. Yeah, and I think even the downsampled every 1 second, that's still very stylish. And it's more interesting because it's sustainable. It's the more important thing. Like you're not going to have to pay such a large bill anymore. So that's great. So thank you very much. Yeah, you've got a few questions in, so I've marked them as we're going to just answer them during the Q&A. So yeah, please keep those questions coming. I'll share my screen. We'll go back to the slides. Where are they? There we are. So let's talk a bit about the impact. So I think Thomas went through kind of the impact, how beneficial it is to have this in place and how it drives machine learning models and like predictive, like anomaly detect, things like that. So um, let's go over one of the case studies. So we have a customer called Cloud NC that we've written about. So when we send this presentation deck out, you'll get all the links to be able to read these case studies as well. So Cloud NC, they operate CNC machines, which are computer numerical control machines. So they transform a piece of material like wood or stone or metals into a shape that has been coded, that has been done through
Tom,
coded
sorry, I
instruction.
think you're not sharing the screen. Uh,
Oh,
I can see it.
is it popping up? Oh, okay. Might be, maybe I'm lagging out a little bit. Hopefully, yeah. Okay. If you're able to see it, okay. Just let me know again if you can't see it. But yeah, so they have machines that will cut out and form different shapes, and they're used by customers who need to build anything from spaceships to smartphones. So CNC machines are extremely important in industrial setting. They were able to improve the efficiency and maximize their production capacity. They deployed predictive maintenance. They also deployed machine learning models that would create like a 3D model with the requirements and figure out the optimal cutting paths so that you would reduce wastage of the material. So that's a really interesting use case. We've got another one from one of our partners in FluxDB for LBBC Technologies. So they're the world's leading manufacturer for autoclaves. So autoclaves are these machines that use pressurized steam for sterilization. So you would normally use them in settings like in biotechnology for sterilizing Petri dishes and jars. In this case, in this industrial setting, they're using it for high performance casting. So for their aerospace customers, you may have things like turbine blades that need to be cast with special material, and they require an autoclave to do the casting. So all of their machines go through a PLC and they connect through to InfluxDB in the cloud, and this enables them these use cases such as anomaly detection and predictive maintenance. A growing trend that we're seeing, and it's a common trend actually with some of our larger customers as well as our smaller customers, but especially our smaller customers, is that you're finding that building your own infrastructure and building your own platform team is really costly. Like it can be measured in months. Sometimes it takes like more than a year, but you've got to build up a platform team with a number of employees to look after that. So the cost and the risk of a project succeeding, that will go up. But with something like Quix Cloud, they're able to do that really quickly because Quix takes care of the platform and the infrastructure and the DevOps. So you've got your engineering and your data teams. They can start building these applications really quickly and start centralizing that data. So you get to unlock all these use cases. Like one of the most common ones is predictive maintenance. And I'll summarize now because we're coming to the end of the session, and I want to leave some time for the Q&A. So if you like anything you've seen there, please book a demo. That's basically the first steps to how a lot of our like developers or our customers get onboarded. They work with us and we build out a POC, or they do a free trial so they can explore it themselves. So please hit the book a demo button at the top of our webpage if you'd like to do that. And go and read our blog post. We're talking a lot about the challenges in the industry at the moment. So data historians is a very important subject that comes up time and time again. So we talk about those as well, and we'll be having those in future webinars too. And Thomas mentioned he will share that repo, that GitHub repo for that project that he just demonstrated today. But we have this thing called Quix templates, which basically are turnkey reference pipelines. So data pipelines that you can just like deploy immediately, and they'll start performing and fulfilling one of the common use cases that you see in industry. So you got a lot of different ones. We played around with AI as well, but all you need to do is spin one of these up and just configure where you want the data saved, certain parameters like the downsampling frequency, things like that. And with very minimal coding, you can get started on a project. So yeah, I'll just call out the predictive maintenance one. So we've got one on there. So check that out. We are simulating basically a 3D printer in this one. And I hope you enjoyed this webinar. But if you'd like to catch up with us again and see more, we're going to do hopefully one a month, maybe even two a month sometimes. So if you'd like to check those out, go to quicks.io/events. And yeah, you'll see the ones coming up. So the next one's going to be about data historians. And as Thomas mentioned, yeah, please do stop by the community Slack. There we've got a mix of like different practitioners who are both like beginners and experts with stream processing, with industrial IoT. We've got people from time series databases who hang out there as well. So lots of different types of personas in there. So come along, check us out. We've got a great help channel where the team are ready and on standby to answer your questions. So you can find us there. And also check out Quick Streams, which is the open source Python library that was being demonstrated earlier. So thank you very much for your attention. We've got a few minutes left, so I think we're going to head straight to the Q&A. So Thomas, you probably can answer some of these questions. Someone asked a question about joins at the beginning, so I've already answered that. So joins is coming this quarter, right? That's the most
Yeah,
requested feature, I believe.
yeah, that's the case. I see when it's expect to merging feature for branches to be live. So that's basically coming from with joins. So with the joins, we're going to be having a merge, and we already have a branching. So you can already split the pipeline, and merging and joining coming in the Q1. Was there a stream processing system? No. So, well, the system that runs on the cars that calculating these inherited parameters are very low level and has a lot of limitations. Um, for example, you have only 80 milliseconds of computation time. So if you get delayed by more than that, you're losing the data. So it's obviously have to run on board of the ECU, so it's quite limited. I see that somebody asking about Panda data frames. That's a very interesting question.
Yeah, we
So
get this a lot. Like Quick Streams looks just like pandas, and I think we've written blogs about it that you'll see. But that's the first thing people notice. They go, "Are you actually using pandas data frames?"
So that's the intention, that it looks like pandas. And basically, the idea is that the quick streams are sort of between a batch and real time, and you don't have to switch your muscle power, muscle,
Memory.
yeah, muscle brain that you learn in batch. So you're working with the data at rest. You load data to Jupyter Notebook, you analyze them, you perform operations, and then you can do similar operations on a real-time data. So that's where the pandas-like API is coming from. Of course, you can use pandas inside QuickStream's library, inside QuickStream's service. At the end of the day, it's just a Python service running in a Docker, which is then deployed to Kubernetes. So for example, if you create a window operation using our newest feature called collect, and you get 100 timestamps per window, you can convert that to pandas data frame. And if your model, for example, expect pandas data frame, you can do that conversion very easily, just data frame from dictionaries and load that into pandas. So that's definitely possible.
Yeah, it's something
Mhm.
people ask about. Like polars comes up as well. People ask about that. So usually what I say is the same thing you say, which is like the Quix data frames are their own type of data frame, but you can convert them to polars data frames really easily. And yeah, we've got a bunch of people asking about SQL interfaces as well. So you can obviously run SQL on top of polars. That should be more performant than pandas. So yeah, check that out. So
So the
I think we're
question
on to the
from
last question. Yeah.
the question from anonymous attendee. So it's asking about stateful processing, and that sometimes you need the previous value, which is 100% correct. So we have two ways of working with the stateful in the stateful way. One is the window operations that I showed you today, where you can accumulate data in a time bucket, and then you get ability to aggregate this data into something: mean, min, max, median. You can just call ML model, whatever. The second way is you can use our stateful API, which is managed. It's under the hood, involves changelog topics, RockDB, and a persistent volume in Kubernetes. All of that is abstracted from you. Checkpointing. So it makes sure that your state is not corrupted, and when there's something happening, it will rebuild. That is quite useful for things like cumulative sums, integrals, where you need to calculate the delta between the timestamps, or you can do rolling windows as you mentioned. We call them sliding windows. So you slide the window with the messages. Yeah, so just search in docs for either windows or apply where there is a stateful toggle on it.
Yeah, and also check out like we recently released a collect function as well. So before you had to deal with the accumulator using the reduce function. So collect may be a more efficient way to do it. So it depends on your use case, but yeah, always check out our latest releases. Like we're continuously releasing new features that would hopefully help you to have things more efficient and fast. So yeah, check that out. I think we've got one time for one last question, which just came in as well. Can you join a
Yeah.
normal stream with states from a window?
Yes, you can. So one of the way how to do that is to use our option current instead of final. So I showed you in the demo a final option where you get a window just when the window is closed. But the current will give you intermediate window state. And then what you can do is just take the incoming row, state of the window, and blend it together. So for example, you can do things like you create a new column which has the version of some columns just smoothened based on a bigger time period. So smoothing some sensors is one example when this is very useful.
Yeah, and with the functions as well, like we have a top level apply function where you can pass in any sort of function, and in that you can inject in a state object. So you have like your own state management as well if you choose to do it that way. So yeah, there's lots to go there. Yeah, but we're almost out of time, so I think we got to wrap this one up. So thank you everyone for attending. Thank you for your attention and your questions. The best thing I can recommend is to find us on Slack. We pretty much live on there, so follow that Slack invite. Say hi, ask your question again, and yeah, we can take it from there. So that'd be the best thing. So thank you, everyone. Hopefully, we'll catch you on the next one. So thank you again, and we'll hope to see you again soon. Bye bye.
Bye bye, everyone.